with cyclohexane. In the big lecture hall here, these models don't project that well, and the models that are big enough to project well are very flimsy and they fall apart when I try to do ring flips and stuff like that. So I thought I'd just make this little video to see if we can get a better picture for the things that are going on with the chair conformation of cyclohexane. Okay, so this model here that you see right here in front of you, it's a type of model where the bond angles are rigidly 109.5 degrees, so any deviation from that is going to produce some sort of strain in the molecule. And about the worst conformation we can have for cyclohexane is flat cyclohexane. And I'm actually having to force this molecule to actually make it flat because it's turning the 109 degree bond angles into 120 degree bond angles. But it's also introducing some other things here. Let's look at two adjacent things, okay? Two adjacent carbons. When it's perfectly flat, notice how we got torsional strain, so that's bad, okay? But it's also bad to have the bond angles at 120 degrees when they want to be 109, which is 120 degrees, of course, is the perfect hexagon. All right, so cyclohexane does not want to be planar because of torsional strain and angle strain. We can get rid of that by just puckering it up here. The conformation that you see here gets rid of most of the angle strain. This is called the Boak conformation, but it's not the best conformation. Let's look at some of the problems with the Boak conformation. Okay, so these two little things that I'm holding here, the red and the white ball, they're getting dangerously close together. So we have these interactions here, which are called Prowl interactions. But more importantly, look right here at these two carbons and these two carbons right here. They're eclipsed. That's bad. Lots of torsional strain in the Boak form of cyclohexane. We find that if you're actually holding the model, you can see that the strain is decreasing when you bend it a little bit, okay, from the ideal. And this is called the twist Boak conformation, but it's still not the best conformation of all. The best conformation of all that gets rid of all the torsional strain and nearly all the angle strain is the chair conformation. And I'm going to twist this molecule into the chair conformation now. Okay? All right. So here is the chair conformation. If we look at any two adjacent carbons, I'm going to try to hold them so they're straight up aligned with the webcam here. Okay, look at that. Perfect staggering of any two adjacent carbons. No matter what I do, every set of carbons is going to be like that. Okay, all right, so again, I'm going all the way around the ring, trying to stagger these things, and yes, they're staggered. Okay, all right, so chair cyclohexane has almost the perfect bond angles, and it has no torsional strain. Everything is perfectly staggered. All right, so when we put a molecule into the chair conformation, notice some deals that I have going on here. I got three of these white things, white hydrogens here, going straight up. And I got three more that are going straight down. Okay, and we're going to refer to this orientation as the axial orientation. Okay. All right, and we got six more hydrogens that are going kind of off to the side, and these are the equatorial hydrogens, okay? All right. Notice that when, let me hold this so that it's, yeah, so that you see the Newman projection there. Two axial hydrogens on adjacent carbons like that are going to be anti, whereas two equatorial hydrogens on adjacent carbons like these two red ones here are going to be gauche. Okay, and if we look at the equatorial, like here, relative to the axial one on the next carbon, okay, it's about a 60 degree bond angle, or 60 degree dihedral angle also, and so that's also gauche. Okay, all right. All right, so we've established that the red ones are all equatorial, and the white ones are all axial. They're either pointing straight up or straight down. I can turn the molecule over and just interchange that. All right, we're going to do another process here called the ring flip, okay? So look at these two carbons I'm holding here. So we're going to do a simultaneous rotation around two of them, and I'm going to flip this one up, and at the same time I'm going to hold the same two carbons, and I'm going to flip the other side down. All right, I get to another chair, but look at this. All the red ones are now axial. The red ones are either going up, down, or they're going either straight up or they're going straight down. And the white ones are now going off to the side, and those are the equatorial ones. So this is the cyclohexane ring flip. And in the cyclohexane ring flip, we totally interchange all axial and equatorial positions, okay? All right, so what used to be equatorial is now axial. What used to be axial is now equatorial. Okay, we can ring flip back, same process. Now we got to the other conformation, where other chair conformation, where now the white ones are axial and the red ones are equatorial, just like what we started with. Okay, you can feel this if you have the model, but molecule kind of gets strained intermediate between doing these ring flips. So there's a little bit of an activation energy to do a ring flip. But as far as, since all we're talking about here is hydrogens, these two conformations, regardless of whether red is axial or white is axial, since they're all hydrogens, these two conformations are obviously of the same energy, okay? All right, so they're not of the same energy, however, when we have methylcyclohexane. So let's do that. All right, so I'm going to put methylcyclohexane here. I just turned one of the hydrogens, swapped it out for a methyl group. And this methyl group, as you can see in the first first rendition of this model, this methyl is obviously axial. This hydrogen on the same carbon here is equatorial. I can do the ring flip, and the methyl is now equatorial. And turns out that these two conformations that we just looked at are not equal in energy. Okay, this one has the methyl equatorial, ring flip it, and here the methyl is axial. Well, it turns out in the axial there's some additional nasty interactions between the methyl group hydrogens, or the electron cloud generally of the methyl group, and the axial hydrogens at the third and fifth carbon. We refer to this type of interaction right here as a 1,3 diaxial interaction. To avoid the 1,3 diaxial interaction, of course, methylcyclohexane can just do its ring flip, and it's not axial anymore, it's equatorial. And in the equatorial, this really doesn't get near any of the other hydrogens. So the methyl group is much happier in the equatorial position. And this is a general phenomenon that the larger something is, the greater its preference for the equatorial position. Okay, so the ring flip, let's just remember it. We're going to do a simultaneous rotation around the two, we'll say if we call this C1, we'll say 2, 3, and 5, 6, or 6, 5. We're going to simultaneously rotate there and rotate again at the fourth carbon, and that'll turn, and that'll do our ring flip. Okay? All right. So cyclohexane does ring flips between the two chair conformations. The chair is the most stable conformation. Bond angles are nearly perfect. There's no torsional strain. When you put a methyl group here or any other group, the axial and equatorial positions, whether they're axial or whether they're equatorial, makes a difference in the overall energy of the molecule. And we see that the larger the substituent here, the more likely it is to prefer the equatorial position. And the measurement of this equilibrium is actually a measure of the sterics of the system. Okay, there's value assigned for the difference, energy difference between axial and equatorial, and that number in kilocalories per mole is defined as something called the A value, which refers generally to the steric size of any substituent. So methyl is, let's see, let me get it back to another chair. Okay, it says the axial methyl is 1.8 kilocalories per mole higher in energy than the equatorial methylcyclohexane. Okay, so that's the end of this video. And again, I was just trying to show something that I tried to show in class, but I don't think it projects that well in a large lecture hall. Okay.